In this video, we will show the dataset for the Gauss function and regress it to the linear polynomial regression to the 8th degree. We will also generate the expansion using SERIESSUM. It's Taylor Maclaurin Series expansion. Let's generate the Gauss function itself. So array formula, Gauss function of the x values. And here's the trend line of the Gauss function and the regression, polynomial regression, where we have the regression coefficients 0, B1, B2, B3, B4, B5, B6, B7, and B8. We'll calculate this regression coefficients using LINEST. Next, we use the error function, the Gauss error function, to calculate the Gauss function. So begin with the error function of the x values. This is the function in red. We factor in, first we factor in 0.5 and square root of 2. Let's start with the square root of 2. So we divide by square root of 2. So that's error function divided by square root of 2. 2. Now we're closer. And we factor in, there's 0.5. So we factor in 0.5. 0.5 times. Now we are in the same line. So they are exactly the same. This is the formula for Gauss. Gauss function is equal to 0.5 times error function of x divided by square root of 2. We will use the Taylor Maclaurin Series expansion. We'll still use 0.5 and square root of 2 factored in. Taylor Maclaurin Series of the expansion of the error function is 2 over square root of pi times the coefficient times x to the power 2n plus 1. The 0.5 is factored in here, and the square root of 2 is factored in here. And the values of the coefficient we can calculate for n values starting from 0 to 1, to 1 to infinity. In this case, we'll just limit to our dataset. You can still get a good approximation. So let's calculate the coefficients. We begin with the denominator. So RA formula, 1 over, there are two factors in the denominator. So inside the denominator, factorial of the n values. That's the first one. Times, okay, what's in here? That's 2n plus 1. 2 times n plus 1. Now that we have the numerator, then we can work on the numerator. So it's negative 1 to the power n. Now we have alternating signs of the coefficients. Now we can calculate the Taylor Maclaurin series expansion. Let's begin with the error function first. So it is this 2 over square root of pi times the coefficient x to the power 2n plus 1. We already have the coefficient. So this is equal to series array formula, series sum of the x values to the power, what's the starting power? So At 0, x will be raised to the power 2 times 0 plus 1. So that's 1. So our value for n is 1. Followed by the value of m, the increment. So next value will be 2 times 1. So the value of n is 1 now. 2 times 1 plus 1. So 2 plus 1 is 3. So from 1 to 3 to 5. So the increment is 2. And last, the coefficients. Enter. Then we can enter the factor in the 2 over square root of pi. So we can factor in 2 over square root of pi. 2 over square root of pi. I think we have that already. Next, we multiply the 0.5. Oh, we haven't added these square root of 2 inside. Now we have to factor in square root of 2 and 0.5 now. So we can get the Gauss function. So this is divided by square root of 2 and multiplied by 0.5. Now we have all the three. So the blue and the red lines are now covered. And we check the regression coefficients. They're all the same. B1 is 0, B2 is 0.339, B0 is 0 or 0, B1, and B2 all 0, B3 is 0.0656, negative 0.06. They're all the same. B4, they're all zeros. B5, 8.79 times 10 to the minus 3, they're all the same. B6, they're all zero. B7, that's negative 5.98 times 10 to the minus 4. This one is 5.97 times 10 to the minus 4, but that's very small. And B8, they're all zero. We'll calculate this regression coefficients using LINEST. To do that, we begin with the 1 comma x matrix. So this is the 1 column, this is the x column, x squared column, and so on. So we will add the power. So transpose of the n values. So we have x to the 0, x to the 1, x to the 2 column, x squared column, x cubed column, and x to the 4th column, x to the 5th, and so on. We'll generate this 1 comma x matrix. So array formula of the x values to the power 0. That's the 1 column. We lock the reference. So we can complete the 1 comma x matrix. So now that we have the 1 comma x matrix, we can now use LINEST to calculate the regression coefficients of this tree. So begin with the Gauss function. RF LINEST of the x data y and data x. So just use this column, data x. In the next video, we will include this column to calculate for the y hat. So That's these are B0, B1, B2, B3, B4, B5, B6, B7, and B8. And they also match to this. So second column will be LINEST, data Y, and data X. Still we have the exact same values because they have the same values here. The third column will be the expansion, the Maclaurin series expansion. So LINEST, data Y, and data X. Something's wrong. Yep, very good. Oh, this is wrong. You'll notice B0, they're the same. B1, 0.3987, they're the same. B2, they're all zero. And B3, negative 0.0656. 4, they're the same. B4, they're all zero. And B5, they're the same. Negative positive 0.879, they are the same. Times 10 to the minus 3. B6, they're all zero. And B7, there's all that's negative 5.98. Well, this one is negative 5.97, but still a very small error. And B8, they're all zero. So this completes the use of series sum and LINEST polynomial regression to generate the data set of the Gauss function, and using also the Taylor Maclaurin series sum function.